Okay, hello. For my presentation, we're going to be looking at the Hough transformation. Now, when I see it, I always want to call it the Hough transformation, but apparently it's pronounced Hough transformation. Anyway, the Hough transformation is a mathematical transformation used in modern machine learning algorithms for detecting shapes from images. Before we dig in, let's take a look at a practical application. Some of you may have heard about a company called Orbital Insight. They've been in the news a lot lately using machine learning on satellite images to track the world's changes due to the COVID-19 pandemic. As we all know, one of the big changes that's been occurring is the increase in global oil supply. As you can see here, Orbital Insight automatically scans the entire planet to identify and track new floating roof tanks as they are discovered, enabling them to develop the most comprehensive global storage number. How do they do this? A floating roof tank uses an airtight lid that rises and falls based on its crude oil storage. Orbital Insight measures the shadows from these tanks and are able to calculate the storage at over 26,000 oil storage facilities and translate those into volume numbers. However, before they could ever measure the volumes of these tanks based on the shadows, they had to do something much more fundamental. They had to locate all of the tanks. Locating all of these tanks manually by looking at each satellite image in the world would be monstrously tedious, and keeping this tank inventory up to date manually would also be virtually impossible. Therefore, creating machine learning and deep learning methods to locate these oil tanks has become a hot topic of research, and it pays off. This slide shows how much it costs to access Orbital Insight's oil volume data, $25,000 a year. So because of all of this, I became interested in studying the machine learning methods used by companies like Orbital Insight to automate tank detection from satellite images. So let's look at the latest publications on this topic. These three papers show the state-of-the-art in automated oil tank detection from satellite imagery. Two of these were published in 2019, one of them in 2014. These papers describe three different approaches to the same problem. These three images, one from each paper, show the results of how these three approaches achieve the same result: to identify and locate oil tanks. And these three images show overviews of the deep learning methods each paper takes to accomplish these goals. We're not going to go into detail on this, but as you can see, each paper takes a different approach. However, as I read these papers trying to understand the fundamentals of how this is done, one similarity keeps appearing between all these approaches, and that's the Hough transformation shown here, here, and here in each paper. So, what is the Hough transformation? And this brings us to the scope of this presentation. In this presentation, we're going to go all the way back to Hough's original patent, published in 1962, and explore Hough's math and methods, along with one very important improvement on his method. Now, Hough, in my opinion, is really an unsung hero of modern machine learning. Since publishing his original patent in 1962, his transformation has been used in many, many machine learning applications. Despite this, Hough himself doesn't even have his own Wikipedia page. So if anyone wants to take on the task of getting Paul Hough a Wikipedia page, I support you 100%. Even though he doesn't have a wiki page, his transformation does have a page. So let's start by looking at the wiki definition of the Hough transformation. The Hough transform is a feature extraction technique used in image analysis, computer vision, and digital image processing. The purpose of the technique is to find imperfect instances of objects within a certain class of shapes by a voting procedure. This voting procedure is carried out in a parameter space, and we'll be talking about that parameter space. The classical Hough transform was concerned with the identification of lines in the image, but later the Hough transform has been extended to identifying positions of arbitrary shapes, most commonly circles or ellipses like the circular oil tanks we saw in the previous example. So let's take a detailed look at the methods in math described in Hough's original 1962 patent. Now, Hough was a physicist, and his interest lied in observing charged particles in bubble chambers, where the charged particles which, when traveling along their path, would leave tiny bubbles, like a trail of breadcrumbs. These bubble tracks create complex patterns, and Hough wanted to be able to know or map which of these little bubbles fell along the same line. However, Hough recognized that, just like picking out oil tanks from satellite photos, that as the number of photographs increased of these bubble chambers, the time consumed by an observer to study them becomes excessive. Hence, the Hough transformation was invented originally to speed up the analysis of the complex patterns created by these tiny bubbles. Interestingly, out of the 3 full pages contained in the text of his patent, only part of the first page is actually used to describe the Hough transformation. The whole rest of the patent describes Hough's quite complex bubble chamber design. The patent also contains 3 figures, 3 images, but only one of these is used to describe the transformation, and the other 2 describe, again, his complex bubble chamber design, which is shown here. We're not going to go deep into this. I just wanted to show Hough's complex bubble chamber design. Therefore, since this patent didn't really, the bulk of it was on the bubble chamber and not the transformation, I think it's safe to say that this transformation had quite humble beginnings. And maybe we're fortunate that Hough's concept was picked up by others and carried forward to become the important machine learning transformation that it is today. All right, enough with the introductions. Let's get to the methods and the math. To do this, we're going to rely heavily on this figure. This is figure 1 from Hough's original 1962 patent. And the first thing we notice here are that there are 2 quote-unquote framelets. And I'll use my mouse here to describe things. You have 2 framelets, 108 and 100. A framelet is a big rectangle here and here. And these framelets can be thought of as 2 rectangular television screens, one stacked on top of the other. In the top framelet 108, we see 3 straight lines called line 102, line 104, and line 106. And we also see a line drawn down the middle of the framelet. That line is called the midline. And then in the lower framelet 100, we see the Hough transformations for each of the lines in the upper framelet, so that somehow the points on line 102 are transformed into this, the points on line 104 are transformed into this, and the points on line 106 are transformed into this. And again, a midline is also drawn across the lower framelet. So what's going on here? Well, what we're seeing in the lower framelet is a transformation of the points that fall on the lines in the upper framelet. So what does that mean? Okay, well, to describe this in the patent, Hough uses a manual geometric approach rather than, an algorithmic formulaic based approach. But this geometric approach, I believe, provides a very interesting understanding of the foundation of what's going on here. So let's walk through it. Later, we'll look how this is done with equations, because that's the approach that's used by machines and machine learning. But for now, let's just look at it and describe it as Hough did in his patent. So if we look at the 3 lines in the upper framelet, we see that they all cross the midline. Now, if we were to find the point for each of these lines that also falls on the midlines, well, Hough would say that these points transform to perfectly vertical lines in the transformed framelet. Next, let's imagine that these lines in the upper framelet extend all the way to the very top of the framelet. Points that fall along the lines at the very top of the framelet would transform to an exactly 45-degree angle line oriented to the right in the lower framelet. Now imagine that these yellow lines are perfectly oriented at 45 degrees. They might not be here because I drew them manually, but imagine they're perfectly 45 degrees. Likewise, if we imagine that these lines extend all the way to the bottom of the framelet, the points that would lie at the bottom of this framelet would transform to exactly 45-degree lines oriented to the left. So again, imagine that these green lines oriented exactly perfectly 45 degrees to the left. So then it follows that if we imagine that a point falls somewhere on one of these lines in between the midline and the top of the framelet, as shown in the patent as figure 110, this point would transform to a line that is in between vertical and 45 degrees to the right. Thus, each line in the lower framelit refers to a point along the lines in the upper framelit and has an angle. These lines have an angle that is proportional to the vertical displacement of the point on the line segment in the upper framelit from the horizontal midpoint of that framelit. Now, another recognized feature is that each line in the lower framelit is made to have an intercept with its framelit's midpoint line equal to its respective point in framelit 108. So let me just stop here for a second to explain what that means. That means where the yellow line crosses the midpoint down here, that point, that horizontal coordinate, matches the horizontal coordinate of the point up here. So this green line, where it crosses the midpoint, that point right there, has the same horizontal coordinate as that green point there. Okay, in addition to that, for each group of lines in the lower framelit, we see that there is a point where all of the lines cross each other. Hough calls this point the knot. This is where all the lines make the knot. To quote Hough, it is an exact theorem that if a series of points in a framelit lie on a straight line, the corresponding line in the plane transform intersect at a point. This point is the knot. And the rectangular coordinates of the knot have a couple of very special properties. First, the horizontal coordinates of the knot equals the horizontal coordinates of the lines where the lines meet the midpoint of the framelit that they are shown in. So the knot is going to match the horizontal coordinate. If I could draw the dotted line right up to that, dotted line right up to that, dotted line right up to that. So the knots match the horizontal coordinates of where these lines are crossing their midpoint. The second important property of that knot is that the vertical coordinates of the knot, where this lies relative to the midpoint line, that is, how far is the knot from its framelit's midline, that distance is proportional to the angle of the lines in the upper framelit. Thus, and you may have to think about this for a second, but the coordinate locations of where these knots fall give the slopes and the intercepts of these straight line segments. Okay, now if that seems a little bit difficult to understand, let's look at it using something that we're much more familiar with. Oh, there you go. I did draw the pink lines showing the knots match the locations of those points. But let's look at it in something we're more familiar with, and that is the equation of a line. Now we all know that the equation of a line is y equals mx plus b, with m being the slope, b being the intercept, and x and y being the coordinates of points that fall in that line. And we can solve this equation for b equals negative xm plus y. And if we put these in graph space, we see the graph at the top. In the graph at the top, we see the axes labeled x and y, as we are used to seeing, and the purple line can be described by the equation y equals mx plus b. As x changes, y changes, but m and b stay the same. However, if instead we change those axis labels to be slope and intercept, but keep x and y constant and change the slope and intercept, and we look at a range of slopes, a range of intercepts, then every point that falls on this line is going to get its own line down here. And the point where these two lines cross define the slope and intercept of that line. And this is really the essence of the Hough transformation, that we can find points in space, we can put those here, into this graph space, and it'll create lines, and wherever those lines cross, if they cross, it'll say where those points are lined up in a straight line, where those cross, that gives you the slope and intercept of that straight line. So this is all great, but using slope and intercept actually causes a couple of problems. And those problems are that the slope and intercept vertical lines can't be described because, for example, they have no intercept. Also, slope and intercept are unbounded, so that, for example, with near vertical lines, it can have an intercept near infinity. But fortunately, y equals mx plus b is not the only equation that we can use to define a line. Instead, we can use something like the Hess normal form. And for the Hess normal form, this is the equation for defining a line based on the Hess normal form. We still have x and y for the points along the line, but instead of using slope and intercept, we define the line by r, its distance from the origin, and the angle theta. So instead of x, y, b, and m, we do a Hough transformation based on x, y, r, and theta. And this works better because r and theta are now bounded. Theta is between 0 and 360, and r is just going to be the distance of the line from the origin. And now the graphs that are produced by this are slightly more complicated. So to illustrate this, I found a great website that's able to visualize this. So here we see the graph, and along the x-axis you have theta, and along the y-axis you have r. So if I go into this one and I put a point, say right there, and you can see you have a straight line. It's showing all the options. So you can put a straight line anywhere in that point because it's just one point. And when you put that straight line in the point, you see the graph that's produced here. So if I put another point that's in a straight line with that one, 2 points will create a straight line. You'll see when this line goes through both points, you're going to create a knot. Boom. So you get a knot. And if I were to put a third point, it's going to cross it right there at the knot also. So this knot is from this knot, you can get the slope, intercept, everything you want from this line. Now what happens if I put a point outside of this straight line? Let's put one right here. And you can see it's not going to cross, and it's not in a straight line with these three, so it's not going to hit the knot. It will, however, when black is in a straight line with blue, you'll get just a 2-string knot right there. Really nice visualization to show what's going on. Okay. Finally, to help further reading and your understanding, if you're interested in taking this deeper, I just wanted to also finish my talk by showing these 4 Sentinel papers on this topic, which takes the Hough transformation and extends its capabilities, not just from being able to detect straight lines, but also being able to detect curves, arbitrary shapes, and circles. And here I also provide a link for you to view the visualization, the interactive visualization that I showed earlier. Thank you.